So a couple of more little things we need to finish up before we get into measurement conversions. We're probably not going to start that until next week. But for right now, I want to look at some of the other operations. And we saw one of them in one of our example equations here in the last hour. We've talked briefly about that. What does that mean? 8 cubed, or 8 to the third power. And how would we calculate it? It's 8 times 8 times 8. That means 3/8 multiplied together, which would be 512. Well, for right now, we're less concerned about how to calculate it than we are how to work with it. So what we're going to do is this. Instead of using 8 to the power of 3, we're going to use x to the power of 3. And of course, that just means x times x times x. So what if we had x to the third times x to the fourth? Well, the x to the third is just 3x's multiplied together. X to the fourth is just 4x's multiplied together. If we multiply them all up, we get, well, there's 7x's multiplied together, x to the seventh. If you look at that, you might realize that there's a shortcut for this. Rather than writing this all out, you could have just taken the powers and added them together. 3 plus 4 makes 7 to get x to the seventh. So if I have y to the 8th times y to the 14th, I'm going to get y to the 22nd. Very good. We have something like this, x to the 5th divided by x to the 2nd. Now that is divided by, but I wrote it like this on purpose because remember we've mentioned that division and fractions can kind of go back and forth. A division problem can be written as a fraction, and a fraction can be thought of as a division problem. So I wrote it like this on purpose because we're going to treat this division like it's a fraction. X to the 5th is 5x's multiplied together. X squared is just x times x. And now, in any fraction, we can cancel out common factors, or we can divide the top and bottom by the same thing. So we can divide out an x here. We can divide out another x. We're left with nothing on bottom here except for 1. And on top we have 3x's, or x to the third. So x to the third over 1, or just x to the third. Now again, if we look at this, you might be able to pick out a shortcut. What we could have done is just taken the powers, 5 and 2, and subtracted them to get 3. So we might have y to the 15th divided by y to the 9th, and we're going to come up with y to the 6th. Good. 15 minus 9 is 6. We could also have something like this, x to the third to the 4th power. If we think about that, that is, bless you, that 4th power means that there are 4 of those x to the thirds multiplied together. X to the third times x to the third times x to the third times x to the third. And we can break that down. X to the third times x to the third, of course, is just x to the 6th, adding the powers. X to the 6th times another x to the third is x to the 9th, just 6 plus 3 is 9. Times another x to the third would be x to the 12th. Now this one's a little bit more difficult to see, but if you look closely, again, there's a shortcut you could use with just the powers. Here, when you're taking a power to another power, you could multiply them. 3 times 4 makes 12. So if we had y to the 8th to the power of 5, that's going to give us y to the 40th. Good. Which brings us to a big question. What's that mean? X to the power of 0. Okay, some of you know that's 1. Very good. A lot of people would want to say 0 at first to that. The question is, how does it equal 1? Remember, that power is telling us how many of these we have multiplied together. X to the fourth meant we had 4 x's multiplied together. How can you multiply 0 x's together? And why would that be equal to 1? Well, according to the definition of a power or an exponent, that whole thing really doesn't make any sense. Having something to the power of 0 doesn't make sense. So just like multiplying two negatives where the definition didn't work, we had to find a pattern. The same thing is going to happen here. We have to find a pattern to define that. And to do that, we're going to go back to numbers for a second. We had 8 to the third power, we said was 512. 8 to the power of 2, that would be 64. 8 to the power of 1 is 8. Now looking at this, when I start out with an 8 as the base of my exponent, it appears as though every time my power goes down by 1, my result is divided by 8. Here the power goes down by 1 again, the result is divided by 8. So if we keep going, do 8 to the power of 0, the power went down by 1. If I divide that 8 by 8, I get 1. So that's why anything to the power of 0 has to be 1. No matter what it is, to the power of 0, it's 1, because it fits this pattern. Now, the next step would be to keep going with this pattern. What would it mean to have a negative power? 8 to the power of negative 1. Now again, you can't have a negative number of 8s multiplied together. But if I continue the pattern, if I divide by 8 again, what's 1 divided by 8? 1/8. 8 to the negative 2, if I divide by 8 again, that'd be 1/64. 8 to the negative 3, 1 over 512. You might be noticing a pattern here. If you look at 8 to the power of negative 3, 8 to the power of positive 3, 8 to the third is 512, 8 to the negative third is 1 over 512. So if I were to tell you that 8 to the fourth is 4,096, bless you, any guesses what 8 to the negative 4 is going to be? 1 over 4,086. So the negative power is just a reciprocal. 8 to the power of negative 4 will be the reciprocal of 8 to the power of 4. Just 1 over. Well, why are we concerned about powers? Well, the whole structure of our number system is based on these exponents, or powers. We talked about our place values. How they're ones, tens, thousand, ones, tens, hundreds, thousands, and so on. But where did those come from? Well, they came from exponents. The decimal system is often called a base 10 number system because the place values are exponents with a base of 10. 10 to the power of 0 is 1. 10 to the power of 1 is 10. That's the tens place. 10 to the 2 is 100 for the 100s place. 10 to the third is 1,000. 10 to the fourth is 10,000. I mean, keep going. Going the other direction. 10 to the negative 1, that's the 1/10th place. 10 to the negative 2, that's the 1/100th place. 10 to the negative 3, 1/1000th place, and so on. Our place values are powers of 10. Now, a lot of times you go to abbreviate numbers, especially if we're talking about financial. Let's say that somebody has $2,800,000. A lot of times we'll abbreviate that and just say 2.8 million. But there's another way we could abbreviate that happens in medical and in the sciences a lot. Or to keep going here. Rather than saying 2.8 million, we would say 2.8 and name the millions place value, which is the 10 to the 6th. And that's where our scientific notation comes from. It's just that. We take the first digit of the number and we name its place value, the 10 to the 6th place. Then we make that the only digit in front of the decimal point. So instead of 2,800,000 becomes 2.8, and then millions, 10 to the 6. So if I have 41,000, we can do the same thing. The 4 is in the 10 to the 4th place. So we're going to make that 4.1 times 10 to the 4th. Or if we had a decimal, 0.00025. 10 to the negative 4, 10 to the negative 5th. We find there's the first digit that isn't a 0 is the 2. So this would be 2.5, and that 2 is in the 10 to the negative 4th place. So 10 to the negative 4. Now, I don't expect that you're going to draw out a number line and label it every time you convert numbers into scientific notation. But that is exactly where it comes from, is right there. Most of us have never been shown that, however. We've always just been taught a shortcut of moving the decimal point. And in practical terms, when you're using it, that's probably the quickest way to deal with it. For example, instead of finding the 10 to the 6th place for converting that to 2.8 times 10 to the 6th, we would just take our decimal point is here, and we need to move it to here, so it has to move 1, 2, 3, 4, 5, 6 places. And that's where the 10 to the 6th can be found. Now again, that's not really where it comes from, but that'll work every time you do the conversions. So if we have 780 million, to convert that into scientific notation, the decimal point starts out here at the end of the number. We want it here because we only want one digit in front of the decimal point, one non-zero digit. So we have to move 1, 2, 3, 4, 5, 6, 7, 8. So 7.8 times 10 to the 8th. So the same here. We want the decimal point to be here because we want it to be 9.2, exactly one non-zero digit in front of the decimal point. So the decimal point starting out here, we have to go 1, 2, 3, 4, 5, 6. Was that times 10 to the 6th? It's negative 6. How do we know it's negative? Because, well, yeah, you always thought if you move the decimal point to the right, it's negative. It's easy to remember, though. This was a large number, which meant it was in the positive power of 10 place values. This is a small number. It's smaller than 1. It's in the decimal places, so those have to be in the negative power of 10 place values. So we know that has to be a negative 10 to the 6th. Or 10 to the negative 6th, I should say. And then we can convert the other direction as well. We might have 5.3 times 10 to the negative 4. To convert that back into standard or decimal notation, we start out with the 5.3 and we move our decimal point. We go one spot. How many spots are we going to have to go? 4. Am I going the right direction? No, I'm not. That's a negative 4, which means this is a small number. So I have to move the decimal point to make this smaller. So 1. What do I have to do if I can't? There's nothing else to move. Put in zeros. So 2, 3, 4. So that is now 0.00053 in standard notation. Now, something very important for you guys. In the medical fields, they are requiring now that you put the 0 in front of the decimal point. Mathematically speaking, it doesn't make a difference whether it's 0.00053 or 0.00053. But in the medical fields, there have been some issues. You know, in something like this where there's zeros here, it wouldn't be a problem. But if it's like 0.21, 0.21 makes it obvious that there has to be a decimal point there. That, however, it's real easy to glance at that and not see the little decimal point here and call it 21. So it's something they're being very strict on, especially in the nursing program right now. You must put that 0 in front of the decimal point. So how about this one? 1.8 times 10 to the 7th. Converting that back into standard notation. There's 1.8. My decimal point has to move which way, left or right? Right. This is a positive power of 10, which means this is a big number. So I have to move the decimal point to the right to make this bigger. And I have to go 7 spots. So 1, 2, I got to put in a 0, 3, 4, 5, 6, 7. So that is 18 million. Now, if we had more time in this course, we would do some work with multiplying, dividing, adding, subtracting with scientific notation. I'm going to show you an example or two, and that's it. Most of you have already had your chemistry course, which would be where you'd use that the most. But let's say you had 5.3 times 10 to the 7th. I'm only using the parentheses here to separate the two numbers. There's really nothing to do inside there. Times 2.4 times 10 to the 9th. We're multiplying here, so this is okay. If we were adding, if you recall, when we add or subtract, we can only combine things that have the same name. In scientific notation, that's the power of 10. So if we were adding or subtracting, anything that was times 10 to the 7th could only be combined with other things that were times 10 to the 7th. Multiplying or dividing, we combine the names. We don't need to have the same name. So here it doesn't matter. So we would start out combining the counts. 5.3 times 2.4 makes 12.72. And we're multiplying, not adding. So 12.72 times, now here's where those powers come in. 10 to the 7th times 10 to the 9th. What are we going to do with the powers when we multiply? Add them. So 7 plus 9 is 16. Now, of course, we can't leave it like this. We've said scientific notation has how many digits in front of the decimal point? 1 digit in front of the decimal point. So this decimal point has to move. It's 1.272. We made the number smaller, so the power of 10 has to get larger. Made the number smaller by 1 decimal point. Power of 10 gets bigger by 1, so that is 17. Now again, if you haven't had your chemistry yet, you'll go over that more there. Start dealing with moles and stuff like that. You're going to do some stuff with the scientific notation. For now, we're going to let that go, and that's going to be enough. We're going to step back, and we're going to talk about ratios. Ratios are nothing more than a comparison between two numbers. Is everybody in here pre-ADN, or is there anybody that's you're pre-ADN? Anybody that's anything else, any MA students or anything like that? So you're all pre-ADN. So I can't use that as a ratio this time around. I'm going to take a look at the class that's coming in later this afternoon. And I have a ratio of 13 female students to 5 male students in that class. I could write that ratio just like that as a fraction, or I can write it like this with a colon in it, 13 to 5. Or I could actually write out the word 2 if I wanted to, 13 to 5. Any of those is an acceptable form. I tend to use the fraction form just because there are a lot of things I can do with it in that form that I would do normally with a fraction. There are some exceptions, and let's go over some of that right now. For example, if I looked at these tables that you're sitting at, if I wanted to do a length, or let's do a width to length ratio. The length of those tables are 18 inches. The length is 6 feet, so 72 inches. Now, as a fraction, first thing I can do is I can cancel out the inches. I can divide those out. And also, both 18 and 72 are divisible by 18. I get 1 to 4. So I get a 1 to 4 ratio. Now, a couple of things I want to point out here. We reduce that just like we would reduce any other fraction. 2, the units disappeared. The inches divided out. So what we have here, 1/4, is unitless. It doesn't matter whether we're measuring in inches, centimeters, feet, cubits, whatever. For every 1 unit of width, that table has 4 units of length, regardless of what the units are. We might have a comparison of, we might have something like this, 2 feet to 18 inch. Now we set up here the inches canceled out and our ratio became unitless. And that's true. If you look at our first example, we were comparing students to students, so they didn't need units in there. Inches to inches here, so we didn't need units. Now we're trying to compare feet to inches. That is not a valid ratio. A ratio must compare two things with the same units. Exactly. We're going to take those 2 feet and convert it to 24 inches. Now this is a ratio. And now the inches can divide out. We don't need it. 24 and 18 can both be reduced by 6. Give me a 4:3 ratio. So that's one thing that ratios must have, is they must compare two things with the same label or the same units. Now, we said we do a lot of things similar to fractions, like we did up here, reducing this one, and we reduced this one as well. But if this were a fraction, we wouldn't stay like this, as 4:3. We'd want to reduce that to a mixed number of 1 1/3. As a ratio, we never want to do that. Remember, a ratio is a comparison of two numbers. So we have to leave it as that comparison of two numbers. That's the biggest difference between ratios and fractions, is we're not going to break them down into mixed numbers at all. Or if we had a ratio of, well, let's say we had a ratio of 12 to 4. Well, both of those numbers divide by 4, which gives us 3/1. As a fraction, we would change that to just 3. As a ratio, we need to leave that as 3/1, or 3:1, because we have to have that second number to compare to. So what if they don't have the same label? They don't have the same unit. For example, let's say we go on a road trip and we go 365 miles in 7 hours. There is no way to convert miles into hours or hours into miles. So this is not a ratio. They don't have the same units, and we can't give them the same units. This is what we call a rate. So the first big difference between a ratio and a rate is a rate compares two things with different units, where the ratio has to compare two things with the same units. The second big difference between a ratio and a rate is a ratio is often left like this here, is 4:3. A rate is almost always reduced to something we call a unit rate. A unit rate means we want the denominator to be 1. So we'd want to turn the bottom of this into 1. The easiest way to do that is divide by 7. 7 hours divided by 7 is just 1 hour. So do the same thing on top, of course, because in a fraction we have to multiply or divide the top and bottom by the same thing. So 365 divided by 7 is 52.142857143 approximately miles. Yeah, I know, I have too much time on my hands. What does that tell us? Well, obviously, we probably round that off a little bit before that. Yeah, 52.1 approximately miles per hour. And we often will write it like this, where we hide the fraction in the units, the miles per hour like that. In fact, we sometimes will hide it even further and just write mph. We have to be careful with that, though. We have to remember what that means. Let's say that on that same trip, we achieved 27 mpg. What's mpg stand for? Miles per gallon. Whenever we see that, we have to think this: 27 miles over 1 gallon, per 1 gallon. Because this is what that really stands for, and this is the form we need it in so that we can calculate with it. So that we can put it into proportions and calculate that way, or if we're doing dimensional analysis, so we have the units in the right place so that we can work with them and cancel them out. There are all sorts of rates that we see around us. We just saw miles per hour, miles per gallon. One that's pretty important to many of us, dollars per hour. Your wage is a rate. In the medical field, you're going to run into units per hour. You might have a patient that's ordered 5,000 units per hour on an IV. Or since we're on the topic of IV, you might have GTT is the abbreviation for drops. So drops per minute or milliliters per hour. So another important rate involving drops is your drop factor, your drops per milliliter. Tells you, depending on the viscosity of the thickness of the liquid, basically, how many drops of that liquid does it take to equal 1 milliliter of the fluid. So let's take a look at some examples of these ratios and these rates. A common drop ratio, or drop factor is often called, is 12 drops per milliliter. And again, when we see that, you have to think 12 drops per 1 milliliter. Ratios, a lot of your mixing ratios, if you're looking at mixing, constituting a solution for medication, you might have 30 milliliters of saline with 120 milliliters of lidocaine or some other serum. Now there are actually 3 ratios that are being performed here. We have, well, actually it could be 4 if we start flipping around, but we have the ratio of our saline to our serum, the lidocaine, which would be 300 milliliters to 120 milliliters. So again, the milliliters would cancel out. Both the 300 and 120 are divisible by 60 to give us a 5:2 ratio of saline to lidocaine. We could switch that around and put lidocaine to saline, which would be a 2:5 ratio, but that's kind of boring. The other 2 ratios we can get out of this, there's always some total amount. So instead of doing the saline to the lidocaine, we could do saline to total. So the saline is still 300 milliliters. What would the total be? That way, 300 plus 120 is 420 milliliters. Now, of course, that would reduce, cancel out the milliliters. Both of them are still divisible by 60 to give us a 5:7. Now, if you're looking closely, you'll notice we could have just used this reduced ratio here and had 5 over 5 plus 2 is 7. We could have done it that way as well. And then, of course, we could have the ratio of lidocaine to total, which would have been, the lidocaine would have been 120 milliliters to 420, which, of course, will reduce to 2:7 ratio. So when we're seeing a ratio like this, there are always all these other ratios out there. We're going to run into a ratio in the next unit called the dilution or dilution ratio. Let's say it's a 1 in 8 dilution. What that is that it's 1 part concentrate or serum to 8 total parts. Now, usually you have the concentrate or the serum. The other component is what we refer to as NS, neutral solution or normal saline, some sort of sterile water with no medicinal value at all. It's just a carrier fluid. So we have a 1:8 ratio of our serum or concentrate to the total. But what if I wanted to know the ratio of the serum to saline, to the NS? Well, there's still 1 part serum, but how many parts saline are there? There's 8 parts total, and one of those parts is the concentrate. How many parts are left? 7. So it's a 1 to 7 ratio of your serum or your concentrate to your saline. And likewise, you can do saline to total. Well, how many parts? We've already established there's 7 parts saline here, so that would be a 7 to 8 ratio. So once we have these ratios, we can use them to find unknown numbers. So let's say we want to have a 1 in 6 dilution, a 1 to 6 ratio of serum to total fluid. And let's say that we have 130 milliliters of that concentrated serum. We want to know how many milliliters of a solution can we create with that? Well, we can solve this using cross multiply and divide. 6 times 130 is going to be 780. Divided by 1 is just 780 milliliters. Whatever the units are up here, we have to have the same units down here. We'll see you guys next week. Let's say we're told we need a 2 to 5 ratio of substances in a mixture. And we know that we have 140 milliliters of this bottom substance. Finding the missing substance, well, same thing. We're going to cross multiply and divide. 2 times 140 is 280. Divided by 5 is 56. Again, the units would be milliliters. There's milliliters down here, so we need 56 milliliters of that substance. Now, I have to be a little bit careful with the units because we can also do proportions like this with our rates. Let's say that we are infusing 500 milliliters of fluid over 2 hours. And we want to set up that IV to run for 8 hours. How many milliliters of fluid are we going to put in there? Well, cross multiply and divide. 5,000 times, or 500, sorry, times 8 is 4,000. Now the units here don't make much sense, but it's milliliters times hours. We're going to divide by the 2 hours here. 4,000 divided by 2 is 2,000. Hours divided by hours cancels out, so we're left with just milliliters. So this 2,000 milliliters is correct. And we'll see here the units here line up, hours and hours line up, so we have to have milliliters and milliliters as our units. We can use these ratios when we start talking about unit conversion. We might have 100 micrograms equals 1 milligram. That's one of our equivalents. Well, we can use that as a rate, actually, not a ratio. Let's say I want to know what would 0.24 milligrams be as micrograms. Well, I'm going to put the 0.24 here, and I can cross multiply and divide. 1,000 times 0.24 divided by 1. The milligrams divide out, leaving me with micrograms as my unit. It would be 240 micrograms. Or you might have a vial that's labeled recommended dose is 12 milligrams per kilogram. You have a patient that is 70 kilograms. We need to know how many milligrams to deliver. So again, we have to remember that this is 12 milligrams per 1 kilogram. 70 kilograms has to go with the kilograms. 12 times 70 is 840 milligrams. It's technically 12 times 70 divided by 1, but I didn't have to divide by 1. Or let's say on the label it says constitute with 12 parts of the concentrate of the serum in 20 parts water. And we need to know how much serum we're going to add to 50 milliliters of water. So our ratio here is 7 to 20. Why don't I have units on there? Because they're both part serum to part serum, the same units. That means it's actually a ratio, so I don't need the units. Over here, where does the 50 milliliters go? Well, that's parts water, and the 20 was describing parts water, so that goes on bottom. Now, I am going to put the milliliters on there because it tells me what units have to go in my other number. If I have milliliters here, I better have milliliters up here. So now I will cross multiply. 7 times 50 is 350. Divided by 20 is 17.5 milliliters. What do you all think? I can see you guys are starting to get a little tired, and I'm actually starting to mumble a bit myself. So I'm going to give you guys the homework to do here. I mean, if you haven't finished them all, you should probably still take a look at page 53 and 54, 1 through 15, those mixture problems. You could also then take a look, page 60 to 61, and 67 to 68. That's 1 through 47, the odds here, and 1 through 27, the odds there. One of the other reasons I'm ending early is I didn't want to keep going and give you more homework. This one's kind of long. Page 73, 1 through 39, the odds, dealing with the ratios and proportions. Page 78, we talked about percents last unit a little bit. There's a little bit of a review of percents on page 78. And finally, page 84 and page 87, 1 through 31, the odds on 84, and 1 through 39, the odds on 87. If the scientific notation, if it's asking you to do anything other than convert from scientific to standard or standard to scientific, don't do it. We're not going to do any multiplying or dividing with the scientific notation, so if there's any of that in there, skip over it. Okay, with that, we're going to